In this video, we're going to start chapter 5. And chapter 5 is on stereochemistry. So many molecules exist in different three-dimensional arrangements. Sometimes they're said to have handedness. The reason we use that term is if you look at your hands, right, they're similar, right? We have 4 fingers and a thumb, generally, and they're, however, different, right? They're different in three-dimensional arrangement. My left hand and my right hand are basically mirror images of each other, right? While they both have 4 fingers and a thumb, if I tried to line them up, superimpose them, so my fingers and my thumb were, lined up, then my palms and the back of my hand are not lined up. And if I get that part going in the same direction, then my fingers and my thumb don't line up, right? My left hand and my right hand are essentially different, right? They're mirror images of each other. And many molecules also exist in that form. So our amino acids are building blocks of our proteins. They exist as a set of mirror images, and our body, however, only uses one version. The other version it doesn't use. Same with our carbohydrates. Some drugs are like that. I talked about this in our intro video. If you've had bio, right, the whole lock and key part of enzymes, if you try to put the key into the lock backwards, right, it's not going to fit. It has to have a particular three-dimensional arrangement. So stereochemistry is really important. Stereoisomers. This term we've seen already, right? These are molecules that differ only in how the atoms are oriented in three-dimensional space. So molecules that differ only in how the atoms are oriented in three-dimensional space. The ones that we've seen in the past were our cis-trans isomers, right? If I was to look at this molecule, sorry, that's supposed to be a dash, versus this molecule, and I was to name them, right, they're both 1,2-dimethylcyclohexane. The only difference between them is how those two methyl groups are oriented. The one on the left, one's coming forward, one's going back, so they were trans. The one on the right, they're both coming forward. They could both be going back, but they're on the same side, so they're cis. So with the exception of the cis-trans prefix, they would have the same name, right? Same atoms connected to the same atoms. It's just that they're connected differently in three-dimensional space. So cis 1,2-dimethylcyclohexane versus trans 1,2-dimethylcyclohexane. Remember that constitutional isomers, structural isomers, those actually differ in how they were connected. So I could do 1,3-dimethylcyclohexane, and that would be a constitutional or structural isomer of the 1,2, right? These guys differ only in how the atoms are oriented in three-dimensional space from each other. An example of something that's not a stereoisomer, that's not a cis-trans isomer, but is still a stereoisomer, I'm going to draw a tetrahedral carbon here, and I'm going to put 4 different groups on it. So I'm going to put a methyl group, and it doesn't really matter what the groups are. I just want to make sure that I'm making them different. We'll put a hydrogen. Let's have a bromine going back, and then a chlorine. And then if I was to draw its mirror image, so this dotted line is going to represent a mirror, right? It's kind of looking in a mirror at itself. The methyl group is still up, right? If I was to look in a mirror, my head is still above my shoulders. This group is reflecting back my hydrogen and then my bromine. So that would be the mirror image of this one. And these are actually stereoisomers of each other. If I tried to superimpose them on top of each other, I couldn't do it. It would be like my hand example. If I wanted to get the bromines and the hydrogens to line up, then my methyl groups and my chlorines wouldn't. So these are mirror images that are not superimposable. Because they're not superimposable, it actually makes them different. So these are stereoisomers of each other. They're not cis-trans stereoisomers, they're a different type of stereoisomer. I haven't given you the name of the type of stereoisomer yet, but they are stereoisomers. They're actually different, kind of like our left and our right hand, right? If you can imagine in your head kind of spinning it around, right? If I was to take this one and I wanted to spin it so that way this chlorine is in the same orientation as this chlorine, right? So I'm going to take it and I'm spinning it kind of clockwise. You could spin it counterclockwise if you wanted, but we're going to spin it so the chlorine is over there. What's going to happen is this bromine that's pointing back is going to end up pointing out. If you can see me spinning it around. This hydrogen, which is pointing out, is going to end up pointing back. So if I was to spin this, so I have the chlorine in the same orientation as the other one, right? I'm trying to see if I can superimpose them. So now the chlorine and the methyl group bonds, right? They're in the same orientation. What's going to happen is my bromine is going to be out and my hydrogen is going to be back. So then when I try to take this, which is the same molecule as this one, just spun around, and try to line it up on top of this one, right? These parts are going to line up, but if we look, these parts are not going to line up. So not superimposable. And we can look at some models. If you're having a hard time seeing it being spun around, we can look at a couple models here shortly. So molecules that have mirror images that are not superimposable are chiral. We're going to have a lot of new terms here at the beginning of this chapter. So chiral also means that something is optically active. Again, a lot of new terms that probably mean nothing at this very moment to you, but hopefully they will soon. So if you have a molecule and you have its mirror image and it's not superimposable with the original one, they're stereoisomers and they're said to be chiral. If something's chiral, it's optically active. Optically active means that it can rotate plane polarized light. If you have mirror images that are superimposable, they are not stereoisomers, they are not chiral, they are not optically active, and they do not rotate plane polarized light. So if something is chiral, it is this, and if it's that, it does this, right? So chiral molecules are optically active, they rotate plane polarized light. What do I mean by that? So normal light goes in all sorts of directions. It's not oriented in any particular direction. So these are my light beams just going in all sorts of directions. If you polarize it, what that means is you're lining it up in one plane. So this is non-polarized light. This is polarized light. So when we say plane polarized, that's what this is showing. So my light is all just going in one direction here. So it's all lined up on one plane. So you could put the word plane in front of it, right? If it's all lined up on one plane, it's plane polarized. So if I was to then take this light and shine it through a chiral molecule, right? So I'm taking this polarized light, I'm shining it through this organic molecule, and then what happens is it comes out rotated, right? I had it lined up completely like up and down, and now it's been rotated. And it can actually be rotated in two different directions. And what happens is each one of those molecules, right? I have one and I have its mirror image, right? The two different stereoisomers are going to rotate it in different directions. And I don't know which is which, but this molecule here will rotate it in a different direction than this molecule here. So my mirror images that are not superimposable will rotate light, and then each one will rotate it in a different direction. There are some terms that go with this, the ones that rotate it to the left. They're called levitorotary. I don't really care so much that you know the entire word, but we give them an L designation. So I would say it's the L isomer. The ones that rotate it to the right, it's dextrorotary. Again, you don't need to know the whole term, but they're going to be my D isomer. So one of these would rotate it, right, our plane polarized to the left, the other would rotate it to the right, right? One of them would be my L stereoisomer, the other would be my D stereoisomer. You can't tell by looking at them which is which. In order to know which one is going to rotate light to the left or to the right, you would actually have to go into lab and do it. You would use an instrument called a polarimeter, and you would measure the rotation. But one of them would rotate it in one direction, the other one would rotate it in the opposite direction. The name of these, right, I said I hadn't given you the name for the relationship, right, yet. They're stereoisomers, right, but they're not cis-strand stereoisomers, they are a different type. And the name for that type is they are enantiomers. So enantiomers are stereoisomers that are non-superimposable mirror images. Right? If you were to draw one and then draw its mirror image and then try to line them up, you couldn't do it, right? Their orientation in three-dimensional space is different. So enantiomers that are mirror images of each other that are not superimposable are enantiomers. So those molecules I drew up above, those are a pair of enantiomers. They are chiral, right? Because they are optically active. Meaning they do rotate light. The physical properties of enantiomers are all the same except for the direction that they rotate that light. So they're going to have the same melting point, same boiling point, same density, same physical properties. It's just that one is going to rotate light to the left, the other to the right. So these are going to have the same physical properties, which means in a lab setting, they're really difficult to separate, right? We can't separate them based on their boiling point or their melting point, which are common ways to separate them. I can't separate them based on density or solubility because that's the same. So it becomes quite difficult in a lab setting to be able to separate a pair of enantiomers. So same physical properties. Right, same melting point, boiling point, etc. Except that they rotate light in opposite directions. And the only way to be able to observe that is to polarize it. So they're going to rotate light whether it's polarized or not. You just can't tell. So if we line it up in one direction, shine it through our pair of enantiomers, right, it's going to rotate that light. So some physical properties, same physical properties, except that they rotate light in opposite directions. If one enantiomer is your D, your other enantiomer is your L. So same physical properties except for light rotation. They are chiral, and they're stereoisomers that are non-superimposable mirror images of each other. So let's look at an example of that. Okay, so a model for us. So I do have a tetrahedral carbon and I have it bonded to 4 things. It doesn't particularly matter what those 4 things are, right? In the example, I had a methyl group and a chlorine. Here, I just have 4 different colors, but it's 4 different things. So I got this one, and then this one here is gonna be its mirror image, right? So I have the orange is up, right? Just like in our example, we had the methyl groups up. I have my green ones going back, and then these are reflecting to each other, and these are reflecting to each other. And if I try to rotate this one, so that way the green is lined up in the same as this one, right? So I'm going to take this, I'm going to spin it around. I now have my greens and my oranges lined up, but if we look, our purples and our whites don't line up. And then if I wanted to try to line those up, right, here I have my purples and my whites lined up. Let me get my hands out of the way. I don't have my greens and my oranges lined up. So they're mirror images, right? The one reflects back to the other, but they're different. They're going to be a pair of enantiomers, right? They're going to have the same melting point, same boiling point, but one is going to rotate light to the left, the other to the right. We don't know which is which unless we go into lab and measure them. The next question then is, well, how do we know when something exists as a pair of enantiomers, right? How do I know when that's a possibility? So what we need to look for is a chiral center. Be really careful. Chiral center and the word chiral are not the same thing. So that word center after it is really important. Our book does call it a stereogenic center. So if you see this term, it's the same thing as a chiral center. Chiral center or stereogenic center, this is going to be an sp3 hybridized carbon bonded to 4 different groups. If I had an sp3 hybridized carbon bonded to 3 things and then my 4th thing is the same as one of those 3, it's actually not going to be non-superimposable. If I was to make one and then make its mirror image and then try to superimpose them, I can. They're not actually stereoisomers. They're not going to rotate plain polarized light. They don't exist as a pair of enantiomers. So to exist as an enantiomer, I have to have a chiral center. So a chiral center is an sp3 hybridized carbon bonded to 4 different groups. If you have one chiral center, your molecule will be chiral. If you have no chiral centers, 0 chiral centers, your molecule will not be chiral, and instead of saying not chiral, we actually use the word achiral. Right? If it's achiral, it's not optically active, it's not going to rotate light. So if I had a carbon that was bonded to 3 different things and then the 4th thing was the same as one of those 3, so I guess it's not 3 different. I don't have a chiral center, it's not chiral, it's achiral. So achiral means not chiral. So no chiral centers, it's going to be achiral. If I have one chiral center, it's going to be chiral. Right? One stereogenic center, it's going to be chiral. Remember, chiral means it's optically active, it's going to rotate light. So no chiral centers won't rotate light. One chiral center will rotate light. If I have 2 or more, it may or may not be chiral. And we'll learn when and when it won't be in this chapter. But just to make this little list complete, we're going to add it now. Chiral or achiral. It really does just depend. And we will learn what it depends on. I do know that something that's achiral is always going to have a plane of symmetry. So if it's achiral, right, that means it's not chiral. It's not optically active. It does have a plane of symmetry. So I have one here that has my tetrahedral carbon, right, sp3 hybridized, but this time I don't have 4 different groups on it. So I kept the orange and the green, sorry, and then it has 2 white groups. So same orientation as before. I have my orange on top, green on back. And if I look at its mirror image, right, green still on top, going back, orange still on top, I know my colors, and then the 2 whites are reflecting to each other. And then if I take this one and rotate it again, so I just want to grab it differently. So here, I'm going to rotate it to line those up, right? Those are now superimposed. My whites are also superimposed. So these are no longer non-superimposable. These are no longer enantiomers of each other. They're no longer optically active, right? If I was to shine light through one of them, I am not going to bend that light or rotate that light. They do have a plane of symmetry, and this plane of symmetry is actually going to cut right through the green and the orange atoms. So if I was to have a plane, might be easier with a piece of paper, I'm going to cut it like right through here, right? I'm going to go right through these atoms, and then this is going to reflect back to that one. Achiral molecules will always have that plane of symmetry, whether it has chiral centers or not. I want to go through some examples. So I'm going to draw some organic molecules, and we're going to identify chiral centers. And then after we do that, we'll determine is the molecule chiral or achiral. So I'm just going to draw some molecules here. They won't all be cyclohexanes. Draw a couple more here. Okay, so remember a chiral center, what I'm looking for is an sp3 hybridized carbon. So any of these carbons that have a double bond on them, right, that have pi electrons, those are going to be sp2 hybridized. So I'm just going to ignore any of those, right? To be a chiral center, I have to be sp3 hybridized. So I have to have 4 different electron groups on it. So if it has pi electrons, it is not sp2 hybridized. So as I go through these, I'm just going to ignore all of those green ones that I'm probably going to end up not removing very well. Okay. So we're only looking at tetrahedral carbons, right? Carbons bonded to 4 things. And those 4 things need to be different. So I'm going to start not with the first one. Let's actually go to this one down here with fluorine on it. And I know that any of these groups, right, I have 3 hydrogen there, so that can't. This carbon has 2 hydrogen on it, so that can't be, right? I need 4 different things. So I'm only going to consider the ones that have a branch, right? If I look at this one, it has 2 hydrogens. If I look at this one, it has 3 hydrogens. So just kind of as you're learning tricks, if it has pi electrons, it's not sp3 hybridized, so it's not an option. If it doesn't have a substituent on it, then it has 2 or 3 hydrogen, depending on whether it's in the middle or on the end. So I'm not going to consider those neither, because to have a chiral center, right, if I go back up to my definition, it has to be bonded to 4 different groups. And if I have 2 or 3 hydrogen on it, I don't have 4 different groups. So the only ones in this molecule here that are really up for consideration are this carbon and this carbon. So then I'm going to look to see what's attached to it. I have a fluorine. I have this group right here. There is a hydrogen there. Hydrogens do count, right? It is a bond. And then if I go right on this molecule, right, that half, right, this part is different than this part. So fluorine, hydrogen, this part of my molecule and this part of my molecule are all different. So that's going to make that carbon a chiral center. So I usually ask you to indicate them with an asterisk. So I'm going to put an asterisk on that carbon. This next one that I had the arrow on, I have a methyl group on it, right? This group right here, there's a CH3 group. I have a hydrogen, so that's two things. And then if I look in this direction, that side is different than that side, right? It goes this way, and those are different. So it does have 4 different things bonded to it. So that is going to be a chiral center. So I'm going to put an asterisk on that. We'll come back and we'll do chiral or achiral after. Right now, let's just do chiral centers. I'm going to look at this one next. And again, I'm going to ignore this carbon because it's not sp3. This isn't sp3. This isn't sp3. This isn't sp3. So none of those are options. And then this one, I have 2 hydrogens on it. So no chiral centers on that molecule at all. Right? Those are the only carbons I have. I don't have a carbon that's bonded to 4 different things. So no chiral centers. This one, do I have any chiral centers on that one? What are you guys thinking? I'm going to give you a second to try it on your own. Okay, I'm going to give you the answer. If you want to think about it longer, just hit pause. But this one doesn't. This is sp2, so they don't count. Here I do have a group on it, right? I do have a substituent, so I am going to consider it. I have a hydrogen. I have this group, and those are different, but this group and this group are the same, right? This is a CH3. I didn't mean to erase the whole thing. This is a CH3, and this is also a CH3. So those two are the same. So I don't have 4 different groups. So no chiral center on this molecule neither. So no asterisks. This one, I want you to try it again on your own. So please just pause if you want to draw your hydrogens on there and think about it for a minute. And then after you're done, hit play again. Okay, so this one does have a chiral center. Again, I'm not going to consider these ends because they have 3 hydrogen, right? So they're not worth thinking about, right? Because they have 3 hydrogen. I guess that is thinking about it. This carbon, it does have a hydrogen on it, but just like the one we just did, I have 2 CH3 groups. So that is not a chiral center neither, right? It has to be bonded to 4 different things. But this carbon that has the bromine on it, right? I have a hydrogen, I have a bromine, and then if I go in this direction, I have a CH3, and then that's different than if I go in that direction. So that carbon does have 4 different groups bonded to it. So I am going to put an asterisk on that carbon. That carbon would be a chiral center. So kind of in my notation, my asterisk is a chiral center. My ketone next. What do you guys think? And no chiral centers on this one, right? This carbon is sp2, so I'm not going to consider it. This one has 3 hydrogen, this has 2 hydrogen, this has 3 hydrogen, so no chiral centers on that molecule. So going up to these cyclic ones. So when it's cyclic, right? And again, I'm only going to look at the ones that have branches, right? This has 2 hydrogen here, 2 hydrogen here, 2 hydrogen here, and 2 hydrogen here. So those aren't contenders. This carbon, however, has a methyl group and a hydrogen. And then what I'm going to do is I'm going to go left and right at the same time, and I'm going to look to see if there's a difference or if it's the same until my hands get all the way back to where I started. So basically this and this are exactly the same. And then I'm going to look at the next 2 carbons out, right? I'm going around both sides. This side and this side are exactly the same. And then I'm back to where I started. So essentially, if I go this direction, it's the same as if I go in this direction. So that carbon is not a chiral center because it doesn't have 4 different groups, right? If I go clockwise or counterclockwise, it's the same. So no chiral centers on that one. This one, however, this is a chiral center. So I have, again, the hydrogen and the methyl group. But then if I go in this direction, it's different than if I go in this direction, right? This is a carbon bonded to this carbon down here and 2 hydrogen. This carbon right here is a carbon bonded to this carbon and 1 hydrogen, right? It's different if I go clockwise than if I go counterclockwise. So that makes that a chiral center. I will put some of that back. So I am going to put an asterisk on this one. And then I actually have 2 chiral centers on this one. This one's also a chiral center, right? There's a hydrogen on there. And then if I go counterclockwise, right, if I go in this direction, it's different than if I go in this direction. And then of course the methyl group and the hydrogen are different. So that's 2 chiral centers on this one. And then it's going to be a very similar sort of thing for the next one, right? This carbon has a methyl group and a hydrogen, and then if I go counterclockwise or clockwise, it's different, right? This is a carbon with a chlorine. This carbon has 2 hydrogen, right? It's different if I go in both directions. And then this is also a chiral center, right? There's a hydrogen and then the chlorine, and then if I go counterclockwise versus clockwise, they're going to be different. So also 2 chiral centers on that one. So that should be all of our chiral centers. Again, a chiral center, going back up, right? Our sp3 hybridized carbon bonded to 4 different groups. So our next task is to determine are they chiral or achiral. So we're going to use this list. If I have 0 chiral centers, it's achiral. If I have 1 chiral center, it's going to be chiral. If it has 2 or more chiral centers, and we do have a couple of these, we're going to look for that plane of symmetry. So if I have 2 or more chiral centers and it has a plane of symmetry, it's going to be achiral. If it doesn't have a plane of symmetry, it's going to be chiral. So going back down, this first one, no chiral center, so achiral. Let's save the ones that have 2 for last. This one, no chiral center, so achiral. 1 chiral center, so chiral. No chiral centers, achiral. 2 chiral centers, we're saving that one. This one, no chiral centers, so achiral. Okay. So what we're doing is we're looking for that plane of symmetry. So this one has one, right? I could cut it right down the middle, and this methyl group is reflecting to that methyl group. I didn't give you stereochemistry on those methyl groups, so like we're just going to assume that they reflect, right? If they're both, I probably should have, if they're cis, there's a plane of symmetry. Be careful though, I'm going to leave the wedges there, and please put the wedges in your notes because I want you to have that. If I was to make one, and if you're going to do this, just draw it as a separate molecule. If I was to do this, I no longer have a plane of symmetry. That doesn't exist anymore, because what would happen is that methyl group is going to reflect to this hydrogen that I'm now wedging. And then this dashed methyl group is actually going to reflect to that hydrogen that I'm dashing. So be careful. I only have that plane of symmetry if those two methyl groups are cis to each other. Since I didn't draw stereochemistry, I was just assuming that, but please, I want you to have those wedged. So add those so we can see that plane of symmetry. Of all my examples, it's the only one that has that, so I do want you to have an example of that in your notes. So this is going to be achiral because of that plane. I have 2 chiral centers, but achiral. Look at this next one. I don't have a plane of symmetry, right? If I was to try to cut it, I have a methyl group reflecting to a chlorine. So no. So this is going to be chiral. By no, I mean no plane of symmetry. So chiral. It does rotate light. And then if I go down to my last one here, the one with the fluorine on it, I don't have a plane of symmetry on this one neither, right? If I tried to cut it here, not only do I have fluorine in a methyl group, but then here I have 1 carbon, on this side I have 2. So there isn't a way to cut this one where I have a plane of symmetry. So this one is going to be chiral.